Today we're going to look at relations, and I have a nice little definition here that looks a lot more complicated than it is. So I'll read this out and then we'll jump into some examples, and you will see how this works very easily. So a relation R on a set X is a subset of X cross X, meaning it has two elements in X. So we say that if element A, comma B is in this relation, we would write x, r, y, which means that x is related to y. This might also be written as r, x, comma, y as a function, since relations are functions. And it can also be written just as r, x, y if you take a logic course, or if you remember from predicate logic, this is the exact same thing. So you worked with relations before, just not necessarily in this mathematical definition of being a subset of a function. Of course, you don't know what functions are, so talking about relations first can be a little bit confusing, but once we get to functions, you'll see how everything kind of fits in nicely. So let's do an example, just in case you forgot how to do this. If we say xgy and denote x is greater than y, where x and y are in the integer set, then for this 4, 3 example, we would write 4g3, or maybe even g4, 3. And is that true? Is 4 greater than 3? Is x greater than y? And of course, in the first one, we see yes, that's true. For the second one, 6g2, we also see that's true. What about 1g7? Is 1 greater than 7? No. Okay, here's something a little bit more interesting. If we have g of 2.1, 1, is this true or false? Well, here's a problem. We have this x value that is not an integer, when it clearly says x is an integer. So we really just don't make a claim. You could say this is vacuously false or vacuously true, but I would just not make any claims since the conditions aren't really appropriate. It's kind of like putting in an invalid entry and getting a syntax error, that sort of thing. Anyway, so relations are pretty simple as far as defining and checking things. What's really important are these three terms and similar terms. These are relations of relations, I guess. And there's reflexivity, symmetry, and transitivity. These are the big ones we're going to look at. So what does it mean to be reflexive? It just means that for all x, we have x, r, x. Which if we draw a little diagram here, and we label this point x, x is going to be related to itself. So for any given item in the relation, it's going to be related to itself. So for instance, if we have an equals relationship, if we have some element, say 4, is going to be in our subset x, then 4, 4 is always going to be in R, since 4 is equal to 4. So reflexivity is really good, at least to be expressed with the equal sign operator, or the equal sign relation, since equality really is just a relation between two things. Symmetry is also kind of nice. I think this is fairly intuitive. For all elements x and all elements y, if x is related to y, then y is related to x. So if we have two nodes here, x and y, if we see a relationship from x to y, then we are going to get the relationship back that y is related to x. In fact, I should denote the relations we get out of everything with dotted green lines. So if we have x and y and x is related to y, we get y related to x. A good thing for this is inequality. So if we say it is not equal, okay, so if 4 is not equal to 3, then that means that 3 is not equal to 4. So if x are y, then y are x. So that's a pretty nice way of illustrating. We can see reflexivity and symmetry don't necessarily have these same properties, because if we have equality, well, equality, symmetry still holds, but does symmetry still hold in, or sorry, does reflexivity hold in inequalities? And that is a question that I will let you answer yourself. Transitivity is a very important one as well. What this states is that for three elements, x, y, and z, if x is related to y and y is related to z or z, then x is also related to z. A little diagram here. We have some nodes x, y, and z. If x is related to y and y is related to z, then we get that x is related to z. So a good one for this is the less than sign. If we have 1 less than 2 and 2 less than 3, then we can infer that 1 is less than 3. Pretty simple stuff. Now there is one cautionary thing that I should tell you about these relations, is that these do not hold for everything. These are properties used to describe certain relationships. They do not enforce relationships. They simply describe them. So if we have something and say, oh, this is transitive, and we find that the operator doesn't make it transitive, then we can't change we can't force the operator to be transitive. It's something that you list out a bunch of properties, a bunch of elements, and you say, it appears this operator is transitive. And then you conclude, oh, it's transitive. Let's take a look at some operators here. The less than or equals to sign. Are these reflexive? Are these symmetric? And are these transitive? Well, let's put in a couple elements and see. Okay, reflexive says that everything is related to itself. So is 1 less than or equal to 1? Yeah, it is. Okay, well, if we take an arbitrary number, is that arbitrary number going to be less than or equal to itself? Yeah, it's going to be less than or equal to itself because we have the equality and we know that x is always going to be equal to x, so we're good here. It is, in fact, reflexive. What about symmetry? Well, to show something is not symmetric or not some property, we just need to find one example where this isn't the case. So let's have 3 is less than or equal to 4. Okay, that's good. Does it imply that 4 is less than or equal to 3? And of course not. That doesn't work. 4 is not less than or equal to 3. So we say that this equality is not symmetric. What about transitive? Okay, well, if 1 is less than or equal to 2, and 2 is less than or equal to 3, does this mean that 1 is less than or equal to 3? And of course the answer is yes, we do see that it is transitive. Of course you have to do this for arbitrary values, so if we say A is less than or equal to B, and B is less than or equal to C, does it hold that A is less than or equal to C? And you can't find a counterexample to this, so yes, it's transitive. What about this x minus y is not equal to 0 relationship? Of course, this is a little bit trickier, because what does it mean to be x r y? Well, all this means is that x minus y is not equal to 0, so it might seem a little bit, oh, how do we translate that? Well, it's actually pretty straightforward. So let's check the things. Reflexive. Well, this should be pretty simple. If we have x r x, that means that x minus x is not equal to 0. But we know that any number minus itself is always 0, so this can't possibly be true. I mean, let's just pick 5 minus 5 and say that's not equal to 0. Well, that doesn't make sense because 5 minus 5 is 0. So clearly, it's not going to be reflexive. What about symmetric? let's take, let's say the numbers 4 and 3. 4 minus 3 is not equal to 0. Is 3 minus 4 not equal to 0? Well, it seems like this is the case, but let's try something else just to see. Now, here's a question you probably have, so I'm going to address it now. And if you get confused, I really hope you don't, but what if we pick x and y to be the same number? So what if we say 4 minus 4 not equal to 0? Then does that imply that 4 minus 4 is not equal to 0? Well, by symmetry these definitions hold, but what's different from regular logic and conditions is that we simply say, well, if the first part is false, then the whole thing is true. I'm sorry I said it was different from logic. It's the same as logic. Because this first part is false, symmetry still holds. So, yes, this relation is symmetric. Now, transitivity, well, let's see here. If, say, if x minus y is not equal to 0, and y minus z is not equal to 0, does it imply that x minus z is not equal to 0? Well, this is one of those things that I kind of want you to play with yourself, because this is a very good strategy. See if you can find an example where this does not hold. And you're going to find that, well, I'll let you figure it out. I will most likely remember to post the answer in the description of the video. If not, someone remind me and I'll just leave it in the comments somewhere. But I think this is a good one for you to test out because this relationship is a little bit trickier than your normal one that you'd receive on a test, and I think it's a really good way to learn transitivity, because transitivity is not always the easiest thing to learn. Anyways, here's another good one. X equal to y. Let's do the same thing. Reflexivity, symmetry, and transitivity. Well, this one is very obvious, I think. We know that x is always going to be equal to x. If x is equal to y, then y is going to be equal to x by definition. And transitivity, if x is equal to y, and y is equal to z, then x is equal to z. So these three properties should be interesting and obvious. So what's so special about this equal sign? Well, this equal sign creates something called an equivalence class. Which, you have the word equals and it creates an equivalence class. So that's kind of cool. And what this means is that something is symmetric, reflexive, and it is transitive. Any relationship that satisfies all three of these properties is an equivalence class. And we'll talk about more in the next lecture. So I will leave you with the exercise of this x minus y is not equal to 0. But I guess I'll do a spontaneous one here. We looked at x not equal to y. Well, here's a quick exercise. Is it reflexive? Well, of course it's not, because we can't say x is not equal to x. By definition, x is always equal to x. Is it symmetric? Well, if x isn't equal to y, then clearly y isn't equal to x. So we're good on that front. What about if it is transitive? Oh, here's a fun one. If x is not equal to y, and y is not equal to z, does that imply that x is not equal to z? Well, here's the answer. No, it's not transitive. Because if you take x is equal to 2, y is equal to 1, and z is equal to 2, you'll see that, okay, 2 isn't equal to 1, 1 isn't equal to 2, therefore we're claiming that 2 isn't equal to 2. But that isn't true, so it's not transitive, it's not reflexive, it is only a symmetric relation. Now, there are other terms to describe the things going on here, like you can have antisymmetric relations, irreflexive relations. If you want to learn more about those, you can read online, they won't be used here, but there's another good example. So I will see you guys in the next video, and if you have any comments, just leave them below, and I will get to them as quickly as possible.